Welcome again to the Academy. We will be continuing our discussion of Cal 3 topics. This is going to be a discussion or introduction on functions of several variables. A lot of Cal 3 is based on multivariable calculus, which is an analysis of functions of more than one variable. So previously we've been used to functions of a single variable, like f of x, for example. Function like y equals f of x, or f of x equals x squared, something like that, which you can graph pretty easily. Graph something like this, f of x. And basically, this was, you have an input x, goes to an output y, or f of x. And so x becomes x squared, so whatever input you put in, 1 would be squared, 1 squared, which is 1. 2 would become 2 squared, which is 4. And for all x values, pretty much. And so when you have multiple variables, basically, you just have several variables in your domain. So let's do a simple case. For example, z equals f of x, comma y. And so you could graph this by drawing the x, y, and z axes. If you imagine this is in 3 dimensions. So this x, y, and z, and we draw them in this way, so that x sort of coming, you can imagine it's coming this way, sort of out of the board, and y and z. And if you do x and y and z, and you'll see that it actually follows the right-hand rule I talked about earlier. And so we call this a right-handed coordinate system. This is the conventional way of drawing the axes. This is the first octant, just like there's first quadrant in x and y. And so basically you have a similar process. So example here, let's say it's a simple case of x squared plus y squared. And so what will this look like? Well, so now you have x, y, and your new z equals f of x comma y. And so now, let's do some points. So we have x equals 0 and y equals 0. Well, 0 squared plus 0 squared is 0. And 0 squared plus 1 squared is 1. It's 1. 1 squared plus 1 squared is 2. 1 squared plus 2 squared is 5. And similarly, 2 squared plus 2 squared is 4 plus 4, which is 8. So now I can plot these points so I can get an idea of what this looks like. This is 0. And so 0, 0 gives you 0. So here's the origin. And 0, comma 1, that's 0 in the x and 1 in the y. And from this point, you go up 1. And then 1, 0, which is here, also goes up 1. And 1, 1, which would be 1, 1, they also go up 1. So you're sort of starting to visualize this, hopefully. 1, comma 2. Same way, you go out 2 in the y direction. You go up 1. I mean, now you go up 5. Which would be that one. And then 2, comma 2. Should be around here. Go up 8. Maybe around here. So basically, you can see that there are some points here, but it's not very easy to visualize. So some of the ways we can try to understand what this function looks like is to think about what it looks like only in certain directions. So for example, if we set y equal to 0, and we just think about x, so for y equals 0, it should become 0, z equals x squared, which we know that what that looks like. So it's going to be x squared, sort of like that, in the x direction. And now similarly, for x equals 0, we just get z equals y squared, another parabola looking thing. So right now, you see that there's a parabola going this way, another one going this way, sort of like that. And so we can kind of realize what this might look like. It's just sort of a parabola rotated, called a paraboloid. So we can imagine it just looks sort of like this. Kind of like a bowl-shaped thing, going upwards like that. And this is one way to sort of sketch the function here in this three-dimensional space. But there is another way to represent these functions, or to sort of think about them, which is called a contour plot. A contour plot thinks about the function as viewed from above. So we're only looking at x and y here. What we're doing is we're fixing certain z values and we're drawing the contour. So these maps, you could have seen plots like these in altitude maps that show you the height of the altitude of the ground in various locations. So basically what you do is you fix the values. So you say, well, at z equals 0, what do I have? If I fix this equals 0, I just get x squared plus y squared equals 0, which we know is just a circle with a radius 0, which is a dot right here, which we already knew corresponds to the origin, 0, 0, 0. But for z equals 1, we have x squared plus y squared equals 1, which is, we know, a circle with radius 1. So here's z equals 1. Or we can just write 1 next to it. So we know that everything on this line has a height of 1. Basically, you want to have them have equal intervals. So 1, 2, 3. And so z equals 2, 0, 1, 2. This will be the next one. Plus y squared equals 1. So this will be x plus y squared equals 2. And that means that it's a circle with a radius square root of 2, which is about 1.4. So like this. That would be 2. And then the same thing for 3. That's square root of 3, which is something like that. Find the x squared plus y squared equals 4, which is z equals 4. So the height of 4, that would be a circle with radius 2. It's not the best circle, but hopefully you get the idea. Basically, this graph shows the same thing as this one, except if we think about this as looking from above, we can see, well, this has a height of 0, here's a height of 1, so it's sort of like it's getting higher up. And this is 2, and this is 3, and this is 4, so it seems, since these circles are getting closer and closer to each other, it's going up faster and faster. It's like a parabola that's been rotated, which is what we know what it is, because if you make x equals 0, y equals 0, we see that they're parabolas. And so this is increasing at a quadratic rate. But these kinds of contour plots are helpful also in visualizing the shape of the graph. And Well, let's do another example of a function. Let's say f of x comma y is z equals, let's do something like x squared minus y squared. So now, x, y, z axes, so we can try to do a similar technique like we did with the other one. So if we set x equals 0, we just get z equals negative y squared. So every time we have x is 0, we just focus on the z and the y axes. It looks something like this. Negative y squared. It's a parabola and we know what it looks like. So when y equals 0, we just get z equals x squared again. So there's one part going up like this, the other part's going down like this. So it's kind of a strangely shaped function. And the easiest way of visualizing it probably is to think of the contour plot. Maybe that will help. So let's think about, well, first let's do z equals 0. We get x squared minus y squared equals 0, x squared equals y squared. So y. So x squared equals y squared, well, that's the same thing as x equals y, but also x equals negative y, because negative number squared will also give you a positive number. So we actually talk about solve for y equals plus or minus square root of x squared, or plus or minus x. Plus or minus absolute value of x. So it's absolute value, and then positive or negative, so it looks like this. It's kind of a strange looking thing. You can sort of see that it does go through the origin like we talked about here. It seems to be flat all along these lines. So this is 0. So how about z equals 1? We have x squared minus y squared equals 1, which is a hyperbola, if you remember the conic sections, that is horizontal. So it looks something like this. This is a 1. 0 still. Similarly, if we have z equals negative 1, we have x squared minus y squared equals negative 1, or y squared minus x squared equals 1. Multiply both sides by negative 1, which is another hyperbola going this way. So now you can start to see sort of what it looks like. So clearly it's positive this way. We're sort of curving downwards in the y direction, which is what we saw over here as well. And really this sort of looks like a saddle-shaped curve. So if you think about, try to draw a sketch of this one. Looks sort of like bigger. So it looks like this. So kind of think about this. Looks kind of like a saddle, a bunch of parabolas going down. So basically, that's what this looks like over here. So next, let me talk a little bit about going to even more variables. So we could have a function of x, y, and z. And this one is not very easy to draw because we probably need four-dimensional thing, which we can't really visualize, four axes. But we can think about this. We think about one sort of time when this would be applicable, and this is, for example, temperature. So if let's say this room, or a room, you can sort of visualize it like this, in terms of x, y, and z axes, which is sort of like a box, rectangular shape. So let's say this is a room. So every point in the room, you can think about it as coordinates. So every point here corresponds to x, comma, y, comma, z. And the temperature at that point, we can think of as a function. So t of x, y, z. And you would have a high temperature over here. So let's say this is 5. Say 5 corresponds to high temperature, but then somewhere over here you have points that are 2, which is a lower temperature, and here you have -3, which is an even lower temperature. So you can talk about a function, basically, where you put in a value, or put in these 3 coordinates that correspond to a point in space, and then you get out a new value. And so basically that is what a function of multiple variables is. So let me talk about some functions that are pretty basic and that you should probably recognize. Now in 2 dimensions we have, for example, y equals ax plus b is a linear equation. In a similar form, we can say f of x comma y equals z equals ax plus by plus c, for example. This corresponds to a plane in space. So let me show you how this would look like. Let's do an example. Z equals x minus 2y plus 4, for example. So one way of visualizing this plane here is to find the intercepts. So when z equals 0 and x equals 0, for example, we can get y equals 2. So this is y, this is x. We get y equals 2, so here's 2. There's a point when x and z are both 0. If we make x and y both 0, we just get z equals 4. Here's 4. And then if we have z and y 0, we just get 0 equals x plus 4, x equals negative 4. So that would be in this direction. Then you can see that if we connect these 3, we create a little triangle, and if we extend this all the way further in all directions, you get a plane. I'll talk about more about planes and lines in a later topic, and more about how to analyze these functions, especially in terms of calculus. But hopefully this was a good introduction. And one thing I would recommend if you want to see more visualizations of these is to go to the website wolframalpha.com, and then you can see, if you type in an equation like this, it'll show you a graph. It'll also show you a contour plot. So if you want any extra examples, you can just go there. But for now, that's my introduction to multivariable calculus, functions of several variables. So I'll see you in the next video.